Let's now turn our attention to actually graphing the derivative given the function. I'm going to walk you through this, and we're going to look at multiple examples together. And there are a couple of applets that you can try. They're very similar in order to practice this skill. The more you practice, the better you're going to be. So I really do recommend that you use the applets. We're going to look at the curve, the square root of x, whose derivative is 1 divided by 2 the square root of x. You can see the graph of the original function f in blue as it increases from the origin, and rapidly at first, and then slower and slower and slower. It does still increase forever, but the rate of change is lessening as we go to the right. When we look at the graph of the derivative, let's imagine what's happening to the values of the slopes of the tangent lines. When I'm close to the origin, do you see how it approaches the origin? Almost at a vertical line. Vertical line has undefined slope, constant divided by something approaching 0. That means the derivative will be very high and approaching that point like an asymptote. You have a vertical asymptote in the graph at that point whenever the slope of the tangent line goes vertical. Of course, the derivative does not exist at 0 since we can't have infinity. Now, what we're looking at, and you can tell here it won't exist at 0 in the formula form because that would cause 0 in the denominator. As we move to the right, notice that it is still positively sloped, first at rather high numbers, and then at lower and lower numbers. It goes lower and lower and continues to flatten out, but it never goes negative. This means that the derivative function is falling and approaching 0, but the slope of the tangent line stays positive, so the derivative, no matter how low it gets, stays above 0. Let's now compare that to the graph of x squared minus 2x and its derivative 2x minus 2. Notice in this particular graph that the derivative, the line in orange, has an x-intercept at 1. What is happening in the graph of the original function, x squared minus 2x, at 1? That's the location of the vertex. We have a minimum at that value. Notice that the minimum value here is creating an x-intercept in the derivative. Basically, the tops of hills and the bottoms of valleys become x-intercepts on the derivative. And the reason is, as you look at the graph, notice on the far left that the slopes are large and negative. So we start out here with negative numbers that are large in absolute value. As we get closer to 1, the slopes begin to approach the value of 0. They get smaller and smaller, but they're still negative. At 1, though, at that one instant, it goes horizontal. And of course, the slope of a horizontal line is 0. This is why we have an x-intercept in the graph right there. Then on the right side of the minimum, it becomes a little bit positive, and then more positive, and larger and larger and larger, which causes it to increase like this. The derivative of a quadratic function is always linear. When we take a look at these, we want to think about where the tops of hills and the bottoms of valleys are. There's one other type of point that can create an x-intercept in the graph, and that would be on the graph of x cubed. When we look at the graph of x cubed, and I did my best to draw it, notice that the derivatives are very negative here, which means they must be not negative, very steep. and positively sloped. So they've got to be up here, but they get to where they decrease close to zero. So it's got to be coming down like this. At one instant at the origin, the slope of the tangent line actually goes vertical. However, it's not a minimum like on this graph or a maximum on a downward opening parabola. It is instead what we call a saddle point. It increases or decreases and then approaches zero and becomes zero at one point, and then it continues to increase or decrease. When we look at the other side, notice that it starts out a little positive, then more positive, then more positive, then more positive. So low and then higher and higher and higher, which means, you guessed it, the derivative of a cubic is a quadratic. This saddle point also creates an x-intercept in the graph of the derivative, which you can see right here at the vertex of the derivative drawn in pink. Let's talk about the steps to graphing the derivative from the original function. This is a long set of steps, but if you practice over and over, they'll become second nature. First, we locate the places in the original function where it has a horizontal tangent line. Tops of hills, bottoms of valleys, maximums and minimums, and saddle points where it comes up, levels off, and then goes up again. Or it comes down, levels off, and then goes down again. Mark these as x-intercepts on the graph of the derivative function. That's where we start by getting all of the x-intercepts on the derivative. Then we start at the left side of the graph and work our way to the right. Starting at the end behavior, we look at the graph between there and the first x-intercept on the derivative. Is the original function increasing or decreasing? You have positively sloped tangent lines or negatively sloped ones. If they're positively sloped, the derivative is above the x-axis. If they're negatively sloped, it's below the x-axis. Now, if the tangent line at a point is very steep in magnitude, whether it's uphill or downhill, you'll draw that point on the derivative further away from the x-axis. If the value is relatively flat, but still slanted, like an increasing or, well, decreasing, still has a slope that's not zero, but small in value, those get graphed close to the x-axis because the value of the derivative is small. The next thing that we want to look at is if we are approaching something where the graph of the original function is approaching a vertical line at a point, the graph of the derivative will also approach a vertical asymptote at that point, as we saw with the graph of the square root of x and its derivative, 1 divided by 2, the square root of x. If you have a sharp corner or a cusp or a place of a vertical tangent line in the graph of the original, there's no unique tangent line. So the derivative does not exist there. These points will become a hole in the graph of the derivative in the case of a sharp corner or a cusp, or a vertical asymptote in the case of a point of vertical tangency. Then we locate the inflection points. After we've drawn a few dots, we look for the places where the curvature of the graph changes from cupped up to cupped down. This is always kind of a gray area. Without calculus, you can't find that point exactly, and we're not ready to do that. We will do it, but it will be in chapter 4 when we study applications of the derivative. For now, just guesstimate where you think it changes from cupped up to cupped down or the reverse. That place represents a maximum or a minimum in the graph of the derivative. If it's positive and cupped up, and then it becomes cupped down, it was increasing and now it's decreasing, so it's a maximum. If it was cupped down and then becomes cupped up, it was decreasing and then increasing, so that would correspond to a minimum. We have two final points, which is basically repeat all the previous steps between the locations of the x-intercepts on the graph of the derivative, and then try to connect it smoothly. Now, if we have a section of the graph where the graph goes linear, what happens to the derivative at that point? Let's consider this graph right here. In this section right here, it goes linear. In other words, a constant function. The derivative of the constant function is 0, because the slope of the tangent line of a horizontal section is 0. So when I graph the derivative, this one starts out relatively positive, and it looks like it just decreases until I get to here. This point corresponds to an x-intercept. So it must be coming down, oops, not quite, like this. Then it starts going negative a little bit, and then faster and faster till it goes vertical. When it goes vertical, it goes down like that. Now, when I'm looking at the horizontal section, because I know it doesn't exist at a point where I have a vertical tangent line, I put a hole, and then I draw this on the x-axis, representing that the slope of the tangent line on this linear horizontal section is 0. Let's now practice what we're doing. There are two different applets. I'll pause here for a moment if you want to, and make sure that you get the two written down. I put them in here so you can figure out what the links actually are. I'm going to go to the first one, and we're going to take a look at graphing the derivative. You'll see here it says reset the graph, which will give you a different function, check accuracy, which will let you know, and show the results. What we want to do is take the function in black, which is the original function, and move the graph in purple by moving each of the dots to where we roughly think the derivative might be. Now, again, this is a guesstimate. I'm happy if your shape looks like the shape of the derivative, even if they don't match at exact points. When I look at the graph of this function, notice that it appears to have a maximum in here. I'm going to take this point and drag it down to the x-axis as an x-intercept. I don't see any other points that are maximums and minimums or a saddle point. So I don't think I have any other x-intercepts. Start on the left side of the graph and move over to -2. What do I think about this part here? It's hard to tell, but it looks like there might be a slight change in the curvature around this value here. I'm going to assume that there's a change in curvature there, but they're all positive. So I'm going to move this up. Notice that the slope of the tangent line here is also positive. If it's getting bigger and bigger, then this point would be about there. And then it starts to decrease and come back down. This means that I can probably move this one. Let's see if this is relatively accurate. It is positive, but doesn't look as steep as the one here. However, I don't think they're that far apart, so maybe like that. Now, what about at this value right here when it's -4? If I look here, again, the slope is increasing. So I'm going to pull it up. Does it have a place where it decreases? I don't think so. So I think this may need to be somewhere up there. It looks like from this point of inflection, if there even is one, I'm guessing, that it increases till it gets there, and then it's still positive, but it's getting lower and lower until it reaches the maximum in the graph of the original. Then it goes a little bit negative, then more negative, more negative, more negative, more negative as it goes down. That means that at this point, it should be low but negative, and then a little lower and negative, a little lower and negative, a little lower and negative, a little lower and negative. I think it's going to be something like this. I could be completely wrong, but let's give it a shot. Let's check our accuracy. 44%, not great. Let's see the results. Well, it looks like apparently there was a change in curvature here that I missed. But I don't know how you could get that close. It's nice if you can get an accuracy around 80% or higher. That's fantastic. 44%, not so great, but let's check the major things. I have it going up, but I missed the location of the inflection point, which they feel is moved over here. So theirs is coming down from that point. Then I had it decreasing too rapidly, and I missed the inflection point over here. If you reset the graph, it'll give you a different graph where you can estimate again. Let's try this one and see if we can do any better. Maximums and minimums on the graph correspond to x-intercepts. This must have an x-intercept at the origin. Now, I know this one's got an x-intercept somewhere between because I can tell it has to curve. I just can't see it all. All right. So I'll keep in mind that it has to curve between those two. Now I want to look from here up to the first x-intercept. Maybe I should move this up so I can see the x-intercept there between the two, roughly there. This starts out with a really steep tangent line. It's negatively sloped, and then it becomes less and less and less until it reaches here where it has a horizontal tangent line corresponding to 0. Because it's negatively sloped and then approaching 0, it must start out below the x-axis and then coming up. And it looks like it's coming up relatively rapidly. There's no change in curvature, so I don't have a maximum or a minimum in the graph of the derivative. Now what happens on the right side of this x-intercept at -4? It goes a little positive, then more positive, until at -2, it looks like it reaches a maximum. Notice that there at -2, it looks like it changes from being cupped up to being cupped down. I think this will be a maximum on the graph of the derivative. As I move over to this next x-intercept, the values are still positive, but again approaching 0. So this one needs to be above the axis and coming down. When I move to the right side of this x-intercept, and I may have it off just a little, but it looks pretty close. This becomes negatively sloped, first a small value, and then getting larger and larger as I go down. Notice it also seems to have a change in curvature. It's hard to tell exactly where the change in curvature is. I would say at 2 or at 3. Let's see. Ooh, it's really kind of between 2 and 3, to be honest. But I think it's a little closer to 2. So in that case, that means that at 3, it's getting shallow again and approaching my next x-intercept, which is between 4 and 5. Then it becomes slightly positive, and then more positive as it moves off to the right. Well, I don't know how good this is, but we'll give it a shot. Check accuracy, 48%. I'm not doing too well. Let's show the results. My basic shape is correct. What's wrong is I'm not getting the exact values of the derivative, but that's okay. I got the basic shape, and that's what I'm looking for from you. Let's now go back to the notes and we'll practice on some different graphs. Let's practice drawing the graph of the derivative directly on here. I'm going to make my points a little bit thicker. When I come from the right side, this is a slanted line with slope 1. So I know the derivative remains a constant value of 1. So I'm going to label this right here to be 1 and this right here to be -1. This means that coming from this side, it is always 1. I know the derivative does not exist at the origin, so I put a hole. Looking on the left side of the graph, it is also a line, but with slope of -1, which means as it approaches the origin, the derivative is constantly -1, but again, it does not exist at the origin, so I have a hole. This sharp corner caused a jump in the graph of the derivative, and it is not defined at that corner. Let's now look at example 9. In example 9, I have a point of vertical tangency right here at the origin. At that point, the derivative will not exist. Is it a hole or is it a vertical asymptote? Let's look at the slopes of the tangent lines as we move across this graph. Do I have a maximum or a minimum in the graph of the original? No. Do I have a saddle point? No. Well, then I may not have any x-intercepts. Let's see what happens. From the left, it starts out positively sloped, but small in value. And then it increases without bound as it approaches 0. So it starts out a small positive value, and then it increases slowly until about here, where it takes off and goes towards infinity. Now let's look at the right side. On the right side, again, at the far right, it is relatively flat, but still positively sloped. We move towards the origin, it becomes steeper and steeper, but still positively sloped. I must have something that kind of mirrors as best I can the graph on the other side. And in fact, they would be exact mirror images of each other if I could only draw it well. Let's now look at example 10. In example 10, we do have some relative maximums and minimums. Those will correspond to x-intercepts on the derivative. Directly below that hilltop, we'll put an x-intercept. On that minimum, we put an x-intercept. Remember that the tops of hills, bottoms of valleys, and location of saddle points become x-intercepts on the graph of the derivative. Now, when I look at this, I notice it's very steep and positive, and then it decreases to 0. Very steep and positive, and decreasing to 0. Then it goes a little negative, more negative, and then it changes the curvature. Let's locate that change in curvature and say it's there and there. That change in curvature is going to become a low point on this one because it is increasing in magnitude, but all negative. And then it starts to flatten out again to reach 0. So that inflection point corresponds to a relative minimum from higher to lower values. becomes decreasing. When we're looking at this one, it starts out a little positive, more positive, more positive until here, where it starts flattening out again to zero. So it starts out a little positive, a little positive, a little positive, reaches a maximum, and then flattens out to zero. And then from here, it starts out a little negative, a little more negative, a little more negative, and it looks basically like this. This could be the original graph of a fourth degree polynomial, and this could be the graph of a third degree. When we take the derivative of a polynomial, we reduce the degree by 1. Let's now take a look at our next graph, which is a piecewise defined function. We again locate the maximums and minimums, which would be here. Well, it would be here, except it's not defined there, so it's not continuous there. So it doesn't have a derivative there, but it would have been. So I'll make it a hole. And then underneath this one, which looks like it's about there, and this one, which looks like it's about 3. Now, do I have any inflection points? Yes, I've got to have one in here. It changes from curved up to curved down. None on the left portion. I might have one on the right portion about here, kind of a judgment call. Doesn't look like the one on the far right changes curvature. These will correspond to high and low points of the derivative. Now we'll start at the far left and proceed to the first x-intercept type thing, from negative infinity up to around 5. It's positively sloped and steep, but approaching 0. Positively sloped and steep, but approaching 0. Then it's negatively sloped and becomes more negative until it reaches this point. It's not going to have a derivative there because it's not continuous there. So be sure to put a hole in the graph of your derivative in both places. On the right side of that, it would have been a minimum, so it's an x-intercept hole. Then it becomes a little positive until it reaches the change in curvature, and it will increase like this. Then it decreases again so that it can reach the x-intercept, which is the maximum in the function. Again, it goes a little negative, then more negative until it reaches the inflection point where it starts to shallow out again. This portion is going to come out like this, and then it comes up just a little bit. Again, we have a break in the graph because this is not continuous, so it cannot be differentiable. Up here, I'm going to guess that the derivative is about maybe, I don't know, a 3. So I can draw a hole there. The derivative does not exist if it's not continuous, but the reverse is not necessarily true. It goes shallow, approaching 0 right there. So this is going to come pretty much straight down. Then it goes a little bit negative, but notice there's a hole in the graph. That point right there is going to correspond to another hole in the derivative. If it's not continuous, it's not differentiable. I want you to try example 12 and example 13 on your own, then turn the video back on and let's see how close our graphs match. Let's see how you did. This section is all cupped up. I would be okay with you putting a hole here since it's not clear if the function continues. Or you could make it solid, assuming it was a minimum point. Then it increases. It does seem to change curvature around here. And then it comes down, but it doesn't approach 0. So it just comes down a little bit. The next part, notice we have a break in the graph, so it's not continuous. So the derivative has holes. at both pieces. Then it increases without bound, which means the graph of the derivative also has a vertical asymptote. On the right side, we have a zigzag pattern. The first line segment is downhill, which means it's negative. It has a slope of 2, which I can tell from the graph. So I draw an open circle at 0, and then I continue in a horizontal line at -2 to another hole at x=1, because I would have a corner. In fact, it's not defined there. Then I have a single dot here, which I can completely ignore because you don't have a tangent line at a single point. The next segment is positively sloped, but steeper than the previous. It looks like it's about 2.5. So I drew a horizontal line segment between x=1 and x=2. The last zigzag part is also negatively sloped, about value -1/2. So draw a horizontal section at that piece. Now let's take a look at the last graph. This last graph, number 13, has a saddle point right here in the graph near the origin, which means that corresponds to an x-intercept in the graph. It also has a minimum value, which also corresponds to an x-intercept. From the far left to the first x-intercept, the value is very negative, but approaching 0. Very negative, approaching 0. Then it goes a little bit negative again, and then more negative until it changes curvature. The change in the curvature from cupped down to cupped up corresponds to a low point in the graph of the derivative. Then it starts to still be negative, but approach the value of 0, which we reach when x=3. Then from this point on, it becomes a little positive and more positive and more positive and continues to increase. So we can see it goes up like this. I hope that this makes sense to you and that you feel confident in drawing the graph of the derivative. In the next video, we're going to cover the derivative rules, which those of you who have had calculus before are probably saying, finally. Yes, the derivative rules will make our life much simpler as they are much faster to use. Join me for the next video on derivatives.